I'm going to draw a picture of, let's make it a piece of steel. And this piece of steel has a whole bunch of little regions inside it. What do we call those regions? Those tiny little regions inside this piece of steel or iron or whatever it is. Starts with a D. Yeah, good. We call them domains. Now, these domains, we represent them by arrows, but remember, what they really are is regions of similar spins of electrons. So it's not really arrows if you looked at it under a microscope, but we simply represent these regions by arrows. Now, if all of these arrows are pointing in random directions, as they normally are, these are in random directions here. This is a non-magnetized ferromagnetic material, right? Ferromagnetic material is a material that can become magnetized, but this is not magnetized. We know that because the arrows are pointing in random directions. If we want to get it magnetized, we got to get these arrows pointing in the same direction. How do we do that? Well, there's a couple ways. What's the first way? What's the easiest way of causing these domains to become aligned? Point these domains more or less, at least getting in the same direction. Yeah, good. Bring another magnet nearby. Okay, bring another magnet nearby. And when you do that, it doesn't have to be beside it. It can be at the end of it or whatever. What you do there is temporarily align the domains in this non-magnetized ferromagnetic material. So these green domains start pointing kind of in the same direction. It becomes a temporary magnet. Sometimes we call it a soft magnet. It will attract now this other magnet. Now, when you take that other one away, the effect is going to go away fairly quickly. Okay, but it's magnetized at least as long as this red permanent magnet is nearby. What's the other way that we can cause these domains to become aligned? Yep. Yeah, wrap a wire around it and apply an electric current through it. We're going to talk more about that one a little bit later on today. But for now, just know that when you wrap a wire around it, send an electric current through it, that electric current will generate a magnetic field, and that magnetic field that's generated by the wire, by the current in the wire, is going to cause the domains, at least temporarily, to become aligned in this non-magnetized ferromagnetic material. It becomes an electromagnet, right? It's an electromagnet, which you probably built in grade 5 or grade 6 or whatever year you did electricity in elementary school. We talked about 3 laws of magnetism as well, and they correspond roughly to 3 laws of electricity. The first one was like charges, wrong. Like poles repel, right? Trick question. Like poles repel. Like charges repel was the first law of electricity. Like poles repel is the first law of magnetism. So north repels north, south repels south. Second one was unlike poles attract each other. So north attracts south, south attracts north. Good. The third law, if we were talking about electricity, we would say charged objects attract neutral objects. And that happens because of an induced temporary separation of charge. The third law of magnetism says that magnets, or north poles and south poles, magnets, good. Yeah, no, that's good, that's good. Magnets attract non-magnetized ferromagnetic material. So they don't attract just non-magnetized things. Okay, the paper on your desk is not magnetized. Magnets don't attract it. Magnets attract non-magnetized ferromagnetic materials, and that happens, just drew the diagram, right? The last page. It happens because of an induced temporary alignment of domains. So instead of an induced temporary separation of charge, it's an induced temporary alignment of the domains. And that causes whatever it is that's non-magnetized to actually become magnetized, at least for a short period of time, which allows it to attract the other material. All right. We talked about magnetic fields as well. Magnetic field, of course, is a line of influence that surrounds a magnet. Okay, the shape of the magnetic field, if you look closely at the shape of magnetic fields, they should remind you of the shape of electric fields. The first diagram we drew last Wednesday after we did our little activity looked something like this, with a north pole and a south pole. Well, if I replace the north pole and the south pole with a positive and a negative, then the electric field would have looked something like this. Okay, which looks an awful lot like the magnetic field that surrounds what we just see there in the north and the south pole. So a positive is not a north and a negative is not a south, but they're analogous to each other, right? Okay, positive produces an electric field like a north produces a magnetic field, and negative produces an electric field like a south produces an electric field. Magnetic field, I should say. The next diagram will look like this. Of course, we've got a north and a south together in the middle. That causes the field lines to go from one to the other, from the north to the south. Okay, so some of these field lines go around like this. Okay, and then at some point, they're affected more by the south at the other end than they are by the south over here. So they bend over to the other side. Okay, it looks something like this, which if you drew out a positive, a negative, a positive, and a negative, you would find that the electric field looked an awful lot like the magnetic field with the north and the south, the north and the south. Okay, they look pretty much exactly the same. Finally, if we have a north and a north against each other, like this, then we're going to find the field lines leave the north and then get repelled by the other north, kind of like they leave the positive and they get repelled by the other positive. This magnetic field configuration is like if we have a negative and a positive and a positive with the two positives beside each other. Again, they look pretty much the same. How would this change, by the way, if I reverse the polarity of both of these magnets? I mean, it's south against south instead of north against north. How would this picture change? Would the shape be the same? If it was south against south, would the shape of it be the same? Absolutely. Would the direction be the same? No. The magnetic field would go in the opposite direction. And that takes us to the definition of the direction of magnetic field. We defined it in two ways, right? We said magnetic field is the direction that a compass points when placed in the field. We did an activity last Wednesday. We put a compass in a magnetic field and we saw which way it pointed. We drew a little arrow showing which way it pointed. That showed us the direction of the magnetic field. The way that a compass points when placed in the magnetic field. The second way was from north to south. So it goes away from the north end toward the south end. Just like an electric field is the way that a positive charge moves when placed in the field, and from positive to negative, a magnetic field is the way that a compass points when placed in the field, and from north to south. All right? Now, we also talked about the strengths of magnetic fields, which I told you didn't have to memorize these strengths. Just understand that when we're looking at the field strength caused by the Earth, it's weak compared to the other field strengths. Okay, you don't have to remember that it's 10 to the minus 5 Tesla. Tesla, by the way, is the unit for magnetic field strength. Okay, you don't need to remember that a bar magnet is 10 to the minus 2 and the magnetar is 10 to the 11 and an MRI is 15 or 1.5 times 10 to the 1 Tesla. You don't need to remember those numbers. Just remember that, look, an MRI is strong. Okay, it's much stronger than a bar magnet, which in turn is much stronger than the Earth's magnetic field. So kind of remember roughly what's stronger than what. Okay, but don't lose any sleep over remembering the details of this chart that we saw there. Finally, we're just simply comparing the fields that we've looked at so far in Physics 20 and Physics 30. The gravitational field, the electric field, and the magnetic field. Of course, gravity is caused by something with mass, right? The Earth causes gravity. The sun causes gravity. You cause gravity, although not very much, because you have mass. The electric field is caused by something that's charged. Okay, you walk across the carpet and build up a charge in your body, you're going to cause an electric field as well. The objects with charge cause an electric field. And finally, a magnetic field is caused, I don't know why I put this the way I did, caused by a ferromagnetic material with aligned domains. What's an easier way of writing that, of putting that? What's an easier way of filling in that box right there? What's a ferromagnetic material with aligned domains? A magnet. And a magnetic field is caused by a magnet. The direction, well, gravity is always attractive. It's toward whatever caused it. the electric field is attractive or repulsive, it's away from the positive, it's toward the negative. Or you could say it's the way that a positive charge moves when placed in the field. And a magnetic field, of course, is attractive or repulsive as well, defined in two ways: direction that the compass points, and it goes from away from the north and toward the south. Finally, we talked about the Earth's magnetic field. Now, we defined the direction of the magnetic field in two ways, right? It was the way that a compass points when placed in the field. All right, when you stand at the equator right here, and you put a compass in that magnetic field, you're going to find that the compass points towards Canada up here, towards the Arctic. All right, that's fine. Okay, nobody has a problem with that. The compass points towards the Canadian North. But if we define direction of magnetic field as from north to south, then that means this has got to be the north and this has got to be the south. So what we find is that what we commonly believe to be correct about the poles of the Earth is actually not right. Geographically, it's right, but magnetically, it's not. Geographic north is in or near Canada. Magnetic north is not in or near Canada at all. It's 180 degrees away. It's Antarctica. Okay, magnetic north is down here in Antarctica, whereas magnetic south is up here, northern Canada. So what we find is, of course, as we said on Thursday, Santa Claus lives not in the North Pole, but he lives in the South Pole. And the penguins live not in the South Pole, but they live in the North Pole. We've just flipped your world all around. Everything you've ever believed in, Santa Claus lives in the North Pole. It's not true. He lives in the South Pole. Got it? All right, let's say you happen to be searching for buried treasure, and you put your compass on your map here. So you put your compass right here, and it's pointing towards magnetic south, because we know that's where it points, right? What we think of as north and what we often call north, but is really magnetic south. And then all of a sudden you flip the light switch on and, oh wait, the compass points somewhere else now. Or you turn on your iPhone that's sitting over here and the compass isn't pointing in the right direction anymore. Or you flip on some switch that causes an electric current to flow nearby and the compass doesn't point toward magnetic south anymore. So then you flip the switch off and it goes back to pointing where you expect it to point. Then you flip it on and it goes back to pointing in some other direction. Then you flip it off and so on and so on and so on. If you do this and notice that the compass is deflected in a direction other than where you expect it to be deflected, whenever you flip on the switch, then you'll have done something similar to a guy named Hans Christian Oerstend almost 200 years ago. In 1819, Hans Christian Oerstend discovered by accident that there's a relationship between electricity and magnetism. He's got a compass nearby a wire, and when he found that there was an electric current going through that wire, that deflected the compass. It caused the compass to point in another direction. And when he flipped off the current, it went back to pointing the way that it was supposed to. His conclusion from that was simple. The current in the wire wasn't the wire, because the wire was always there, even when the compass was pointing where he thought it should. It was the current in the wire that caused the compass to point in another direction. Therefore, the current in the wire must be generating another magnetic field, a magnetic field that's stronger than the Earth's magnetic field, and therefore causes the compass to point somewhere other than where the Earth wants it to point. So we concluded that electric currents, which is just moving charges, or it could simply be, even just charges moving through the air. Not necessarily in a wire, but electric currents or just simply moving charges generate or produce magnetic fields, which of course causes his compass to deflect in a direction other than the way that the Earth should cause it to deflect. So what does the magnetic field look like here? We drew the magnetic field surrounding a bar magnet and surrounding different configurations of bar magnets, but what does it look like when it's caused by an electric current in a wire, it can't look the same, although there does have to be a polarity, right? A north pole, south pole. It doesn't look the same. Well, the shape of it was actually determined by Oerstend to be circular. I'm going to draw now an electric current coming out of this page at you. We're going to represent that by a dot versus if the electric current was coming away from you into the page, we'd represent by an X. Just like, this represents something that goes to the left, sorry, to the right. This represents something that goes to the left. This is a symbol that represents something coming towards you out of the page. This represents into the page, away from you. How do you remember that? How do you remember that notation? Well, I'll tell you how I remember it. When I was 4 years old, I used to play with a neighbor across the street sometimes, and sometimes we'd go down to his basement because he had a cool basement. There was a pool table in there, there was a dartboard down there, there was all kinds of cool stuff. There was lots of change lying around that we'd find and put in our pockets, all kinds of cool stuff. I remember one day we were playing darts. Now, he was six or seven, I can't remember. I was 4, and we were playing downstairs throwing darts at a dartboard, and we weren't supervised. We were throwing darts at this dartboard, and we weren't very good, especially me, because I wasn't even in school yet. So you throw a dart at the dartboard, and for the most part, it missed. But when it hit the dartboard, usually it wouldn't stick in the dartboard. Once every 20 tries, maybe you might stick one on the dartboard somewhere, maybe. Most times it would just hit the dartboard like this, and then bounce right off, if it even hit the dartboard. I remember this one time, I was picking up darts that I had thrown and either missed the dartboard or bounced off the dartboard. I'm not sure which. I was picking up darts, so I bent over, and then I stood up, and all of a sudden, my friend that lived across the street and was throwing darts at the dartboard managed to get one to stick in. But it didn't stick in the dartboard. It stuck in my back, literally. He threw one and right in my back, and it stuck there. I didn't see it coming because I was turned around picking up the darts that I dropped off, that I had missed the dartboard with. But I can still to this day picture the darts in slow motion, or the dart, I should say, in slow motion coming towards me. And when I picture that dart in slow motion coming towards me, what do I see? The point of this dart, right? It's like a dot. So when I picture the dart coming towards me, I picture this, a dot. I would rather picture the dart going away from me. Okay, that's not what I see in my mind, but I'd rather picture that. If I pictured the dart going away from me, then I would see the feathers or the fins of the dart going away from me, right? In other words, it would look more like an X. So that's how I remember, still to this day, 38 years later, a dot and an X, what they represent. A dot represents something, whether it's a car or an electric current or a whatever coming towards you. And an X represents whatever it is that's going away from you. Right now, we want to represent electrons coming towards us, an electric current coming towards us. The shape of the magnetic field surrounding those electrons coming towards us, as I said, it's circular. Looks something like this. A series of concentric lines. What does the word concentric mean? One circle around another. A circle, then another circle, then another circle, then another circle around it. So it's a series of concentric circles. What do you notice about the spacing of those circles? Are they evenly spaced, Ken? No. Yeah, they get bigger. They get further and further apart from each other as they get further and further away. And that should make sense to us, right? If the field lines are produced by this little dot in the middle, which is an electric current coming towards you guys, coming out of the board, if it's caused by that, then the strength of the field should get weaker as you get further and further away from whatever caused it. And the strength of the field is represented by how close the field lines are together. So you can see here in this diagram that the field strength is getting weaker. Okay, we should predict that, right? What about the direction now, though? What about the direction of the field? We know the shape of it. Okay, in a bar magnet, right, the shape of it looks like this. And then we define the direction as away from the north end toward the south end. It's pretty hard to see a north end and a south end here. So how do we define the direction of it here? Well, we're going to use something called the wire grasp rule. You don't need to draw this picture if you don't want, because I'll explain it here in just a moment. But the wire grasp rule is what's going to allow me to find the direction of that field. The wire grasp rule goes like this. You're going to take your hand, your left hand, if it's negative particles, like electrons, it's going to be your left hand. If it's positive particles, like alpha particles or protons, you're going to use your right hand. So take your left hand, usually, and clench it up like this. Stick your thumb in whatever direction the current is moving. So whatever direction the charges are flowing. So if you take your left thumb right now, and I tell you that the electron is going towards the left side of the room, then you should stick your thumb towards the left side of the room. If I tell you the electrons are going up towards the ceiling, then you should stick your thumb up towards the ceiling. If I tell you it's going towards the mountains over there, then you should stick your thumb towards the mountains over there. Then you're going to clench your fingers. Okay, bend your fingers the natural way. And what you're going to look at is your actual fingertips, like your fingernails. And your fingernails will point in the direction of the magnetic field. By the way, the symbol for magnetic field, I'm going to show you right now, is a B. Remember, the units were Tesla, capital T, but the symbol is a B. So our bent fingers will point in the direction of the magnetic field. So we're going to go back to that diagram for just a second. If you need to write what I just wrote down, I'll go back to that page in just a second for you, okay? But I want to illustrate it real quickly here with the diagram that I just drew. We have the electrons going out of the page towards you guys. So everybody right now, everybody do this right now. Put down your pens. Okay, let's put your left hand in. You ready? Let's get your left hand out. Put your right hand in. And let's shake it all about. Okay, you ready? Ready to go? Now what I want you to do is use your left hand again. I want you to stick your left thumb back towards the back of the room. Because that's the way the electrons are going out of this page, right? Towards the back of the room. Then I want you to bend your fingers like this. Now, how much do you bend your fingers? Is it just like this a little bit? Or is it like this a lot? It doesn't matter. Just bend them. Okay, whatever makes you comfortable, whatever makes you happy. Bend your fingers or whatever. All right, I bend my fingers a little bit, and I got my magnetic field, my fingertips pointing towards the right. I see Simon bending his fingers like this. His fingertips are pointing downwards, right? Well, then how do we resolve the magnetic field that I've just determined towards the right? Simon's is downwards. Well, my fingers are right here towards the right. Simon's are right here pointing downwards. Somebody else might bend them even more. Where are they pointing? To the left. There's no conflict with that, right? There's no inconsistency with the way that I had my fingers pointing and the way that Simon had his fingers pointing. Where my fingers were, the field was to the right. Where he had his fingers, the field was downward. But it continues around in a complete circle. So we'd say in this case, the direction of the magnetic field is clockwise. We just say it's a clockwise magnetic field. And a couple more examples for you here, just with the same thing. If this X represents the electrons, then the electrons are traveling which way? Which way are the electrons traveling if it's represented by this X? Remember, picture the dart. You're 4 years old. This dart, this neighbor of yours is throwing darts at you. trying to kill you. Are the darts going away from you or towards you when you see it as an X? Away from you. So this time, the electric current is going into the page. We know the shape of the magnetic field is going to be circular like this. They get further and further apart from each other. We'll just draw a couple of those field lines. Everybody stick it's electrons. So let's stick your left thumb into the page. My fingers are going to go like this. I don't care where they are. We're going to end up with a counterclockwise magnetic field. Point your fingers right here. Great. Point them right here. I don't care. Doesn't matter. It's going to be a counterclockwise magnetic field any way you look at it. This one we've already done, right? This one, the magnetic field is, so the finger thumb went out of the page. Fingers go clockwise in this one, right? It's the example that we just did a minute ago. This one's a bit harder, though. Here, my electrons are going to the left side of the page. So I'm going to stick my thumb to the left. This pen that I have in my hand right now represents the wire. My thumb is pointing towards the left side of the page, right? The pen is pointing towards the left side. I don't care how much you bend your fingers, but just know where they are. However much you bend them, okay, right now look at my fingers. Right now my fingers are where? Don't tell me which way they're pointing. Tell me where they are. They're right above that wire, right? Which way are they pointing? Which way are my thumb fingers pointing right now? My fingertips. Towards you guys. In other words, out of the page. Which way are they pointing now? Down, right? And they're in front of the wire right now, right? Which way are they pointing now? Into the page. When they're below the wire, and when they're behind the wire, they're pointing up. So we're going to say above the wire, the magnetic field would be out of the page. Below the wire, the magnetic field would be into the page. In front of the wire, I can't remember what it was. In front of the wire, my fingers pointed downwards toward the bottom of the page. And behind the wire, my fingers pointed. If we look at that, if this is my wire and this is the plane of my page, my fingers behind it pointed toward the top of the page or up the page. What we've just done might not seem like too big of a deal, but it is arguably, if not one of the most important, the single most important technology discovery in the history of the world. Everything that we use today, just about everything that we use today, from your doorbell to your iPhone, uses this discovery. The idea that an electric current generates a magnetic field, and a predictable magnetic field. After we practice this a little bit, doing this hand rule and determining the direction, go over one more hand rule. I'm going to show you some examples of how exactly this works in some basic technology applications. Okay, but it's there in just about every bit of technology that we have today. Again, the idea that an electric current generates a magnetic field. And it's only a 200-year-old discovery, less than 200 years old. Okay. Much of what we have today wouldn't have existed 200 years ago, simply because we didn't know that electric currents generate magnetic fields. Okay, here's what I want you to do right now. You take a look, please, at worksheet number 10. I think there's 4 or 5 questions in worksheet number 10. I'd like you to do those 4 or 5 questions on worksheet number 10 right now, please. And then we'll take a look at them as a group when you're finished. Let's take a look at these 5 questions, and then maybe we'll call it a day here. Number 1 says, draw the magnetic field surrounding the wire showing electron current below. So electrons being negative particles, right? You know what I do? Okay, when I see an electron, and we're dealing with the magnetic field doing it the hand rule, I just write down LH to remind me that it's left hand. Because if there's a mistake that is the most common mistake with these questions, it's using the wrong hand. Use your right hand when it's a negative particle, use your left hand when it's a positive particle. This is going to be a left hand. It doesn't look much like an LH, but that's better. So draw the magnetic field surrounding it. Well, we know that it's circular. I don't need to draw 50 lines. 2 or 3 lines is good enough just to show us that it's circular and to show us that the field lines get further apart, progressively further apart as we get further out there. Clockwise or counterclockwise? Well, the X represents an electric current going into the page. It's like the dart going away from you. It's like what my friend, when I was 4 years old, saw as he was throwing darts at me. I don't think he was actually trying to hit me. He just did. But it's what he saw, right? The dart going away from him. So we're going to stick our left thumb into the page. My fingers are going to go counterclockwise. Okay, I don't really care where you draw your fingers, whether it's here or here or here. Okay, it doesn't matter. It's counterclockwise any way you look at it. Next one, also electron current. So also going to be left hand. This time it's coming out of the page. This is what I would have saw if I had turned around and saw the dart coming towards me. It's a good thing I didn't, because he probably would have got me right in the heart and killed me with that dart. This time my thumb is coming out of the page. My fingers are going to go, you can see the shadow of my fingers even right there. It's going to be clockwise in this case. Doesn't matter where you put them. You're just looking for which way your fingertips, your fingernails are pointing, okay, at that particular spot. 3, we get electron current here as well. So again, it's going to be the left hand. This time, let's do it in words, okay? Above the wire, right now my fingers are above the wire. Which way are they pointing? Okay, which way are my fingers pointing right now? Well, right now they're pointing into the page. Right now they're pointing down the page, right? But right now they're above the wire. Right now they're behind the wire. So when they're above the wire, which way are they pointing? Into the page. How many people got that one? Good. Behind the wire, you can see that they're pointing down toward the bottom of the page. Okay, if you're below the wire, it's going to be exactly opposite because it continues around in a circle. Below the wire, it's out of the page. And in front of the wire, they're pointing up the page. 4, the direction of the magnetic field surrounding the moving alpha particle. Alpha is a positive particle, so it's going to be the right-hand rule, the Wiregrass rule. Okay, this time we're going to say to the left of the charge, behind the charge, to the right of the charge, and in front of the charge. Here's the charge. Where are my fingers right now? If this is the plane of the page, this is the plane of the page, where are my fingers right now relative to the plane of that page? Are they in front of the wire? Are they behind it? Are they to the left of it, to the right of it? From you, from your perspective, my fingertips right now are sticking to my lip there. My fingertips are in front of the page, or sorry, in front of the wire, right? Okay, which way are they pointing? Towards the left. Right now, my fingertips are to the left of the wire, and they're pointing into the page. Behind the wire, it's going to be to the right. We know it's going to be opposite, but we can double check that. Okay, right now my fingers are behind the wire. They're pointing towards the right side of the page. To the right of the wire, it's going to be out of the page. How many people got that one right? That one's harder, eh? Is that a little bit harder? Question 3 and 4. Okay, 5 and 6 are pretty similar here. Electron in number 5, alpha particle in number 6. So this is going to be left hand. This is going to be right hand. This is kind of like algebra on the hand rule, rearranging the hand rule. Instead of saying, here's your thumb, which way do your fingers point? This time we're going to say, here's which way my fingers point, which way is my thumb going to go? So here, first one, it's left hand. Fingers are pointing clockwise. Thumb points out of the page. Question number 6, it's right hand. Fingers are pointing clockwise. Thumbs pointing into the page. Done. Good? Yep, Simon? No, number 5 is an electron. 6 is an alpha particle. Oh, did I do number 4 wrong? Yeah, you're right, actually. Yeah, no, you're absolutely right. Number 4 is exactly opposite to what I had, because what did I do? I used the left hand, even though I was careful to write down RH so I wouldn't forget to do that. So number 4 is exactly opposite of that. Thank you, Simon, for pointing that out. Everybody got that? All right. Good. That's it for today, guys.